The ideas in this class are geared to enhance your learning in different settings and spark more creative thought that in turn will help you generate new ideas. As you go through these examples, you'll start to recognize that the general concepts of design blending are all around you. When I ask students what thoughts come to mind when they see this image, I hear comments like pollution, trash, rust, decay. The word opportunity is never in the mix. Then one individual out of a million comes along and creates an industry with only a few basic hand tools. Now, why would I pay over $100 for a rusty top off an oil drum? Because it's unique, it's one of a kind, it's creative, and I like unique, and so do business corporations. Employees like this are adaptable and see solutions where others don't. Here's another example with this drop tank. After World War II, hundreds of these were stockpiled in surplus yards. They were basically worthless and sold for about $40 a piece. Then that one visionary gets the idea that a drop tank could work as an aerodynamic neutral car body. And they've been racing these for the last 50 years. We see examples of this cross-pollination all around us, but often never notice. Part of this green power competition is to build a body over the frame. Out of 100 cars, this was one of the most impressive ones. But the reality is most schools can't afford this. My other really favourite car was this one right here. I took a look at this and I thought, wow, that's just beautiful. It's balanced, it's lightweight. How did they do this? Well, they simply took a cargo rack and dropped it over the car and cut a hole in for the driver. Problem solved. It's quick, efficient, and low cost. And you may ask the question, well, is this cheating? No, that's the sort of person I want to hire. Someone that can save me money, that can see combinations that others can't. And it's really some small few that can recognize this potential in accidental combinations and learn how to play it out. But how do you teach this? In the past 20 years, not much has changed in the way we teach engineering principles. For example, we create a sketch, we draw all these basic parts, put them together in an assembly, create a bill of materials, and then we create the motion, something similar to this. But what we're really doing is recreating a known outline that's already been defined. But when you actually break down what's actually happening in class to its lowest common denominator, we spend a lot of time just copying and modifying. For example, I'll draw a cylinder, the students draw a cylinder. I modify the cylinder, they modify the cylinder. The outline is already defined and we're just recreating a known. And so I asked the students, I'd like you to cross-pollinate with these two objects here, a cylinder and a sphere, and make it your own. Come up with your own interpretation. And initially they're not sure what to do. So I'll just show them an example. Well, something like this. So now I'll say instead of the cylinder, let's just try a cube. Now unfortunately, they start thinking, well, what does he want us to do? What's the professor trying to teach us? And so they're thinking about what's in my head, not what's in their heads. So they'll come up with something like this. But again, that's too similar. I want you to think of ways to make this your own. So can you think of any variations on the theme? How about this? Simply take the sphere out of the center. How about this? You take it out of the corners. Yet I'll still have students who'll say, well, you did the easy ones and I can't think of anything else. Well, are you sure? What if we just take a large sphere out of the top and on the opposite side also? There's a real neat interpretation right there. This is how you make something your own. When you get out of the way and let the students play, it's fun to see what they come up with. In this example, they started with a cube, took spheres out of each corner and the center, and rounded the edges. This student had some in the class quite confused for a moment until he said, "Look, just focus on one color at a time." And it was really easy to see that it was just 3 cubes, just rotated. And surprisingly, the best spatial thinkers are often not the students you'd suspect. With this class quiz, I was dismayed at how many students actually tried to draw this starting with a cube. Now, why are these simple examples so important? Because random combinations drive radical innovation. We've all seen how these random combinations drive innovation in music, in art. Think of the rock band Queen. Growing up, I sure never liked opera music, but I loved the song Bohemian Rhapsody. What'd they do? They combined rock with opera. An odd combination, but in the process they created a classic song. With this image in the top right-hand corner, the gun with the cigarettes in there, you don't need to say a word, you don't need to write anything. You automatically know that smoking is going to kill you. But adding this creativity into STEM? How? That's no easy task. It is what it is. Defined formulas, precision, accuracy. There's only one right answer. Is it really any wonder so many students drop out of engineering and we have trouble retaining creative students? So I continue to look at ways to develop this idea to highlight how random combinations can drive innovation. Here's one example from class. So it's hard for students to get started sometimes, so where do you start? Okay, well, draw the 2 shapes you see, a circle and a hexagon. In what order? Well, just experiment with ideas. Try putting the circles on the corners. What size? Any size. Just experiment with different ideas. And then one student changes the circles to spheres. Spheres on every corner. Then it's very easy to add a large round edge. Then you just slice it in half. Once you have the top, it's very easy to create this base. Then overnight I'll 3D print it and bring it back into class the next day. When the students put the lid on, it just slides around. The first question is, well, how do we get this to stay here? It's also really thick and quite heavy. We didn't need to use that much material. So how about we make it thinner? And I'll explain to you how you use the lip command. But again, instead of me pushing it on the students, you need to learn this command. They're asking me, how do we use the command to get this to lock in place? And then I 3D print it again, put it on the table, then someone drops some apples in there. Quite an interesting innovation. Another thing I like to do is take some boring household item and then add it to a letter, say S. And what do students come up with? Here's another beautiful example. You can see the S right there. They just took the S shape and then mirrored it around. This is actually very simple, but it looks beautiful, very creative. And again, I can't highlight the point enough that I didn't think of this idea. It wasn't in my head. I couldn't have come up with this. The best ideas are in the students' heads. Now, all these conceptual blending examples come out of core engineering principles. In this next case, the helix command. But then I like to take the spring and blend it with something else like a staircase. And let's see what the students come up with. What an interesting interpretation. Here's another example. Again, the spring and the stairs. What's interesting with this example, the student won over $1,000 in cash, and this was on the Stratasys website for over a year. The interesting thing is, it's the same input with two very different outcomes because everyone has a different perspective, a unique perspective. Again, in class we focus on core engineering commands like the loft and the sweep. But I don't stop there. Then I'll take the sweep command and a boring earring and say, let's create a new product. What do the students come up with? Something very attractive, very appealing. Again, they 3D printed this, it fell apart right on the edges. Redo it, reprint it again. And it's easy to take this concept and make it your own. We show the students how this was done, and they'll take it in another direction. Make it their own. Instead of an earring, we've got a Valentine box of chocolates. So it's all about finding connections between unlikely objects. This is what makes creativity happen. And don't get discouraged if you're thinking these designs are too complicated. There's another engineering concept the students need to learn, that there is beauty in simplicity. If you can draw a line and a circle, you basically got this figured out. Go to the helix command, identify the line and the circle, and just rotate that 3 times. Now it looks a little bumpy there, so we'll just add a sphere at that area and pattern that. But again, I don't stop there. I throw it back to the students and say, I'd like you to experiment with this concept, come up with your own variations. What if you used a different pattern number? Instead of 3, 4, 5, let's try 6. What's amazing with this example, that any sequence of 3 reconnects. 3, 6, 9, 12. Now, mechanical engineering is all about mechanisms. So let's combine a camshaft with a robot and see what the students come up with. What a classic interpretation. And you can see that these parts are really quite simple. But when you pattern the original, it looks amazing. And again, the best ideas aren't in my head. They're in the students' heads. And here's a variation on that theme. Here's another simple example from class, the letter Z in a table. So what does a student usually do? Well, he'll take the Z and extrude it. Then I've got something to work with. I'll say, okay, that looks a little thick, and what if we wanted to fold this up, and how would you get a chair under there? So they'll redesign it, and they'll figure out how to slide the chair under. Now, once the student has something on the screen, it's easy to offer suggestions. What if we wanted to fold this up? How could we add a hinge? What if we took a number, a chair, and a desk? Here's another classic student combination. And once the student gets this far, then they start asking more questions. Well, how could I actually build this? What manufacturing process could I use? How much do you think I could sell it for? And once you start to catch on to this concept, you can apply it in other classes. This is from the generative design class. Once you have this interesting shape, what else could you do with it? Turn it into a piece of jewelry, maybe a necklace, and then start taking it in a variety of other directions. So don't believe it if anyone ever says the greatest songs have all been written, the greatest art has all been painted, the best products have all been invented. Hopefully this class will get you thinking along the same lines as Michelangelo, who saw an angel in the marble and had to carve to set her free.